Okay, so the first problem says that a flower pot is knocked off of a balcony 20 meters above the sidewalk and falls toward an unsuspecting 1.75 meters tall man who is standing below. So, how close to the sidewalk can the flower pot fall before it's too late for a warning shouted from the balcony to reach the man in time? We have to assume that the man is below requires 0.3 seconds to respond to the warning. The ambient temperature is 20 centigrade grades. So we have to calculate different things. First, we have to calculate the sound takes to reach the man. No? How much time it takes to reach the man. So we make the difference of heights divided by 343 meters per second. This is a simple isolation of the velocity simple formula, and we obtain 5.3 10 to the minus 2 seconds. As a next step, we have to calculate the difference of times. We have to remember that it had to be showered before the pot falls and can hit. So we add 0.3 seconds plus the previous quantity, and this results in 0.353 seconds. Okay, the fall, it's a simple fall, so we can use the formula of y equal 1/2 of gt squared. So we add the appropriate data and we isolate for t. This results in 1.93 seconds. Okay, so the warning needs to be given at a certain time, no? So as a next fundamental step, we have to subtract 1.93 seconds and 0.353 seconds, and this results in 1.58 seconds. Okay, so now that the pot, when the pot has fall, we now can again use the simple fall equation that tells us that 1/2 multiplied by the gravity multiplied by the 1.58 time, and that equals the 12.2 meters. Finally, we difference of these values of distance that it's above the ground. So we say that 20 meters minus 12.2 meters equals 7.82 meters. The next problem of the chapter 17 is the 26. It tells that two small speakers emit sound waves of different frequencies equally in all directions. Tell us the different data of output of speaker A and B, and we have to assume that only speaker A emits sounds at the first part, the second only speaker B, and the third part that both speakers emit sound. Considering the different data, we can notice that the radius is a thing we have to calculate first. So we can say that RAC equals 3 to the square plus 4 to the square, and we apply a square root to these calculations. So finally we obtain 5 meters. So next fundamental step, we say that the intensity equals P over 4 pi r squared. We substitute with the appropriate data, and we obtained, well, we put here the 5 that we have just calculated, and finally we obtain 3.18 10 to the minus 6, right? So we can proceed to calculate the decibels of beta. So beta equals 10 decibels, okay? And this is multiplied by logarithm of a division of the data we have just calculated over 10 to the minus 12. So okay, we put this this quantity, 3.18, 10 to the minus 6. Okay, as you notice here. Okay, we substitute and we divide by 10 to the minus 12. So finally, if we made the correct calculations, we obtained that the result is 65 decibels. So the next we have to consider that B is emitting sound. So we say that Vc is 4.47 meters, no? It's the same as the previous one, no? The same steps, but with different calculations, different data. So now we calculate the intensity. We say that is 1.50 10 to the minus 3 divided by 4p radius to the square. And we obtain that this result is 5.97 10 to the minus 6. So we have, as a next important and fundamental step, we say that beta equals 10 decibels multiplied by logarithm of the division of the data we have just calculated, 5.97 10 to the minus 6, over the same data that is 10 to the minus 12. As always, with the correct calculations, we obtained 67.8 decibels. This is not over yet, so we have to calculate the C part of the problem. Finally, as in part C, as we are considering that both are emitting sounds, we just add the intensities. So we use beta equals 10 decibels logarithm of the division of the intensity that we have just calculated divided by 10 to the minus 12. Finally, if all this procedure is correct, we obtained 69.6 decibels, but we have to remember that these quantities are in micros, so there are 10 to the minus 6, right? In chapter 16, problem 24, it tells us that it's a speed of 200 meters per second and a diameter of 1.50 millimeters. So first of all, we have to write our formula that says that velocity equals square root of t over mu. So as a next important step, we have to isolate t. So now we substitute, we relationate the data to know that density multiplied by area multiplied by velocity to the square equals, we substitute that the area is p times radius to the square, and finally we obtained a result. If we add correctly all the data, yes, we multiply by p, we multiply it by 7.50 10 to the minus 4 to the square, and times 200 meters per second square. So finally we got that the tension is 631 newtons. This is our final answer of this problem. As we notice, they are simple, they are fast, and we only had to isolate the tension, substitute, relationate the data to finally obtain the tension. In the final problem of chapter 16, the 27, it tells us that the speed is of 20 meters per second, there's a tension of 6 newtons, and it requires to calculate the tension of a wave speed of 30 meters per second. So we put as mu as constant, we relationate it, so we obtain that the tension 2 divided by velocity 2 to the square is equals to tension 1 over the velocity 1 to the square. So this is only because mu is constant, no? So we can do this relationship and we just can calculate the tension number 2. So let's isolate it, and we obtained that tension number 2 equals P2 over P1 to the square multiplied by T1. So we substitute the different data. So we said that tension 2 is going to be equal to 30 meters over second divided by 20 meters over second. This is to the square multiplied by 6 newtons. So the final result is 13.5 newtons. This is our final answer and our final problem.